You know, every single smart device you own, from your phone to your laptop, has this tiny hidden engine inside that makes it all work. For decades, we've built that engine in 3 dimensions, but today, we're exploring a revolutionary new idea. What happens when you make it, well, completely flat? So, that engine I was talking about, it's all built from this one tiny thing called a PN junction. Think of it as the fundamental Lego brick for every transistor, every diode, every computer chip out there. It's the simple, elegant little switch that, when you multiply it by the billions, literally powers our entire digital world.
Right, so for decades, we've built these things in 3 dimensions. But here's where it gets really interesting. Scientists are now asking, what if you could just flatten it? Squeeze it down to the 2D plane? What changes when the very heart of our technology is just a single atom thick?
Okay, so here's our game plan for this explainer. First up, we're going to take a closer look at that hidden engine. Then, we'll dive into the pretty strange world of 2D materials. We'll see how these new flat junctions stack up against the old 3D ones, check out how they perform in the real world, and then, this is the cool part, we'll explore the incredible new ways we might be able to tune the devices of the future. Let's get into it.
All right, Section 1, Electronics Hidden Engine. Let's start with the absolute fundamentals, just to make sure we're all on the same page with the component that started it all, the PN junction.
So what exactly is this thing? Well, it's actually pretty simple. You take a semiconductor, right, and you intentionally mess with it by adding some impurities. It's a process called doping. On one side, you dope it so it has a bunch of extra positive charges. That's your p-type region. On the other side, you dope it to have extra negative charges, electrons, and that's your n-type region. Now, where those two sides meet, they form this barrier, and it acts kind of like a one-way street for electricity. And believe me, it is the most important one-way street in the entire world.
Okay, Section 2, enter the second dimension. Now, let's take that whole concept and just squish it.
What does it actually mean to build this crucial little component on a single atomic layer?
Well, this is what it looks like. It's pretty incredible. Instead of some bulky 3D structure, the entire junction exists on a single continuous sheet of a material like, say, molybdenum disulfide. The p-type and n-type regions are created right next to each other, forming what's called a lateral junction. I mean, this is the absolute ultimate in miniaturization.
All right, Section 3, a tale of two junctions. Now here's a really important point. Making something atomically thin doesn't just make it smaller. It fundamentally changes the physics behind it. So let's put the old 3D world head-to-head with this new flatland and see what's different.
Okay, now this is where we get our first major clue that something weird is going on. This graph is showing the density of charges right near the junction. Now in the 3D case, that's the dashed brown line, you can see the transition is super sharp, really abrupt. But then look at the 2D case, the solid green line. It's this much more gradual, stretched out slope. We're talking a massive difference here, sometimes hundreds of times wider. That's a huge signal that something profound is happening under the hood.
And the reason for that huge difference we just saw? It all comes down to a concept called charge screening. Okay, think of it like this. In a 3D material, the electric fields are all contained inside. It's like a voice in a soundproof room. But in a 2D material, there's no up or down to box them in. The electric fields actually leak out into the space around it, kind of like a voice in a wide-open field. This weak screening is the key. It's the one thing that changes absolutely everything else.
And this slide right here shows you the direct result of that. In the 3D case, see how the electric field drops off in that predictable straight line? But in 2D, because those fields are leaking out all over the place, they follow this much more gradual logarithmic curve. Now this might sound like a super technical detail, but trust me, this single difference in how the electric field behaves is the root cause of everything we're about to see.
So, Section 4, performance in a flat world. Okay, the physics are different. We have established that. But what does that actually mean for performance? What happens when you actually try to use it and apply a voltage?
So this graph shows us how much current flows when we apply a voltage. In a perfect world, a diode follows a very specific ideal curve. The 3D junction, you can see, gets pretty darn close. But then look at the 2D junction in green. For a huge range of voltages, it's behaving in this non-ideal way. What this is telling us is that in the flat world, the weird underlying physics and any real-world imperfections, they have a much, much bigger impact on how the device actually performs.
So what do all these different performance regions actually mean? Let's break it down.
First, when the device is supposed to be off and not letting current through, the 2D junction leaks a little more. That's called generation. Okay, then when you first turn it on with low voltages, the current is dominated by this really inefficient process called recombination. I mean, it works, but it's not great. It's only when you pump in a higher voltage that it finally switches over to the efficient diffusion current that we really want. So the big takeaway here? 2D devices spend a lot more of their time stuck in that inefficient recombination mode.
And this isn't just theory, you know. Let's compare a real 2D material, molybdenum disulfide, we'll just call it MOS2, to good old reliable silicon. And wow, the difference is stark. The silicon junction snaps right to its ideal performance pretty quickly. The MOS2 junction, though, it spends almost its entire operating range stuck in that less efficient recombination mode we just talked about.
So, the crucial thing to understand is this. In today's 2D devices, this non-ideal behavior isn't just some minor quirk, it's a dominant feature. Understanding this and engineering around it is one of the biggest challenges for researchers in this field. But it's not all bad news, not at all.
Which brings us to Section 5, Tuning the Future's Devices. Because you see, these new physics also unlock entirely new possibilities, things that are simply impossible to do with our traditional 3D materials. And, you know, the researchers behind this work say it best. It's the ultra-thin nature of these materials that opens up a whole new playbook for designing electronics.
Here is a perfect example of what they're talking about. This graph shows a property called capacitance, which is basically just the ability to store an electrical charge. Now, in a normal 3D junction, its capacitance changes a lot depending on the voltage you apply. But just look at the 2D junction in green. It's almost perfectly flat. That means its ability to store charge stays constant no matter what. This is a genuinely unique property you just don't see in 3D.
So why should you care? Why does that matter? Well, for the engineers designing high-frequency circuits, think about the radios in your phone. Having a component with a stable, predictable capacitance would be an absolute game-changer. It could lead to much simpler and more reliable designs.
And check this out. Here's the other superpower. Remember how we said those electric fields leak out? Well, this graph shows that you can actually change the junction's performance just by changing the material around it. Let that sink in for a second. You can tune the device's electrical properties without ever touching the semiconductor itself. This gives engineers a completely new knob to turn, a new tool to design with.
Okay, so what about speed? This slide is looking at the potential for radio applications. Now, right now, MOS2 doesn't quite match the speeds of highly optimized silicon, but what's really promising is that by increasing that doping we talked about earlier, its performance can be pushed well into the gigahertz range. That shows there's a clear path forward for making future high-speed 2D electronics a reality.
So let's tie this all together. At the end of the day, 2D junctions are not just smaller versions of their 3D cousins. Their weak charge screening creates totally different physics. And while that makes them more sensitive to real-world issues, it also unlocks these remarkable new properties, like that constant capacitance and the amazing ability to be tuned by their environment. They really do represent a fascinating new frontier for electronics. And all this leaves us with one last, really fascinating question. For decades, progress has meant cramming more and more 3D transistors into a smaller and smaller space. But as we start to hit the physical limits of that approach, maybe, just maybe, the next great leap forward won't come from building smaller, but from thinking flatter.